Improve the performance, but all the work was done with static configuration. StarPU is about doing that in real time and detecting actually how to spread the load on all the computation devices you have on your computer. So GPUs or CPUs. Okay, Samuel.
Thanks. So good afternoon, everybody. So StarPU is a project that we've been working on for several years here in Bordeaux at the INRIA laboratory. So there are a few people working on this. So it's mostly the work of Cédric Ogonnet, who is not here anymore, but we are continuing the project. So you're in Bordeaux. So the Runtime team, our research team, has been in Bordeaux for like a decade now. And the interesting thing with Bordeaux is that we have wine, of course, and it just means that we've been doing parallelism for centuries, actually. The vineyards. So parallelism, nowadays we have a lot of cores, and big cores, small cores. We don't really know what we will have in the future, so the Xeon Phi is about a lot of small cores. We still have some big cores. So we don't know exactly how, but most probably we will have heterogeneity, like we have at the moment, probably a bit different, but with FPGAs or Xeon Phi, we don't know, but probably heterogeneity. And the question is, how do you program these? In the past, you would use just pthreads and maybe OpenMP TBB to make that programming easier, but mostly threads, and that worked well for CPUs. And then when we had some GPUs, well, we wanted to use other languages because it's not really the same. So we had CUDA, and then OpenCL was proposed as a standard. Is it really what we will use in the future? We don't really know. There's OpenACC as well. For us, the biggest concern with all of these is that it's mostly an offload model. That is something you want to make faster, you push on the GPU, you wait that it finishes, and then you get the result. What we would like is taking the benefit of both the CPUs and the GPUs at the same time as much as possible. I would like just to mention the OpenMP programming model. I will talk quite a bit about programming models. So the idea of OpenMP is that you have a for loop and you know that it can go in parallel. So you just say that to the compiler. So it's mostly a fork join approach. So you have a fork at the beginning of the for loop. It goes parallel, and then at the end of the for loop, it's just one thread again. And then OpenMP3 introduced some notion of tasks. It wasn't so easy to get that into it. So it's not so pretty, but anyway, there are tasks, and that's interesting. You can, with that kind of programming language, extend that to GPUs by putting some other pragmas to say, this will go to the GPU, but again, it's mostly an offload, and it's quite hand-tuned in that you would map the matrix to the GPU, or you would copy it explicitly, and it is the kind of thing that we don't want the programmer to express by hand, because then you cannot optimize these transfers. With OpenACC, it's mostly the same, so you see that it's explicitly copying the matrix. We don't want that. So we would like to have both multicores and accelerators taking advantage of everything, but the difficulty is that you have everything happening at the same time, and you have synchronization and distribution of data that you have to manage. So I've mentioned tasks. Task graphs are something that theoreticians have been studying for a long time. And in the mainstream languages, usually you wouldn't have this, and people would consider that it departs a bit from the usual sequential programming, so they wouldn't like this. But still, it's a really nice way of expressing parallelism. You see the parallelism here. Does that really depart from sequential programming, actually? Let's take an example. So this is the actual code, even if simplified a bit of an actual computation that people like to do for high performance computing. So whatever it means, you have a for loop with some operation on some parts of the matrix. And so here we express that this function will read and write some piece of the matrix, and then this other operation will read the same piece of the matrix. And so we have a dependency, a data dependency from here to there, because this will read what that has written. And this is a sequential code, actually. The programmer can write this and test that it works, but it's actually a parallel one. So if we just unloop the whole thing, so we have a first operation, and then we have a dependency between the second one and the first one. We have a few of them like this, and then this operation will depend on some of these, and that as well. And just inferring the task graph from the sequential source code is extremely easy, just by following the data dependencies. And then we have our parallelism. So that's a really nice way of getting something parallel from a sequential source code. And then once you have this, you just wait for all the tasks to complete. So that's what we are using at the moment in the StarPU project. So it's a uniform way. How do you express it? With perhaps a compiler with some directives. It's not clear what is best. I will show some example. But the idea is that you have one way of expressing it, and you don't care about does it execute on a CPU, on a GPU, the data transfers, etc. So this is where we put ourselves in the stack here. There are some HPC applications and there is some hardware, and usually we don't talk directly with people writing applications. We talk with people which build compilers or write some linear algebra applications and things like this. And we tell the operating system, don't do anything, I will handle the scheduling, basically. And the idea is to take the most of the informations from the application or from the libraries. Quite often it's more the libraries which know for this kind of application it's better to put priorities here rather than there. Or the compiler may have detected some things at compilation, and then we take this information into account to optimize the execution. And conversely, once the application has executed, we collect some feedback, whether the bus was quite busy, whether there were idle times and things like this, to tell the application this is where it happened not so well. And one thing we would like to manage to do in the future is getting the scheduling theoreticians to put their theory that has not really been used in the mainstream runtimes into an actual runtime. So we are starting to manage this. So the idea of StarPU, we have this machine with a lot of CPUs, a lot of GPUs, and we have a NUMA machine, so we want to avoid this kind of cross-NUMA transfers and things like this. And so we want to execute dynamically on the tasks because we don't know in advance the application, we don't necessarily know how it will behave on the architecture. And we want to eliminate the transfers, not only avoid this kind of transfer, but also avoid transferring the same data several times, of course, which is something which is not done by the previous examples I've shown. When it is explicit, well, the programmer can remember, I will not transfer several times, but he has to think about it. Here, we want to do this automatically. And for this, we use a software virtual shared memory. I will talk a bit about it later. So this is how it looks like. So we have the data management on one side and the scheduling engine on the other side, and they discuss a bit for decisions. And then we essentially have several drivers for CPUs, GPUs, SPUs, whatever PUs. So that's why the name StarPU, all kinds of processing units. So our idea, our main idea in the team is trying to do dynamically what you cannot do statically anymore. By this I mean linear algebra people have been writing their library for multicore and they did it by hand. And then they had one GPU. Okay, they did it by hand again. It was tedious. And then they were asked for several GPUs, and then they say, no, we cannot do that by hand anymore. It's really too complex. We don't want to spend the human time on this. And so we do that for them. And the idea is that the application just pushes a graph of tasks, and then we manage this. So I said we use a virtual shell memory. The idea is that the application will register its data to the runtime, and then it will be up to the runtime to know where the data actually is. Maybe there are several copies here and there because it's used in several places. Maybe there is just one because it has just been modified, so there's just one valid copy. So StarPU handles all of this. And then when you have a task here, actually its inputs and outputs are references to virtual shell memory data. And so the application doesn't have to care whether the data is on the GPU because it was computed there, or in the main memory, or maybe on the disk, or whatever. And so what tasks are, it's simply references to some data, and then several implementations, so that a task can complete either on a CPU or on a GPU or something else. The application can just provide all the versions it has, or maybe just some of them, because the port is not complete, but at least it can run. You have the CPU version, and you will do the GPU version later. And our idea is that then we have a nice tool for theoreticians to play with a scheduling algorithm. So I won't talk a lot about this, more on the graphical side. Just to make sure you understand, StarPU doesn't actually compile code. It just takes the function pointers you give to him, and that's all. So maybe you use a library, so you have the CPU version and the GPU version, and you provide both pointers, or you use a compiler which will compile into both versions, some same code. Probably you will want to tune, but at least, like with OpenCL, you have one code which can be compiled into both CPUs and GPUs. And so in the end, it really looks like this, as I've shown, thanks to the implicit dependencies between the data. We actually get this task graph and we can schedule it. So just to give some figures, so it has started like 6 years ago. So it's mostly a PhD thesis and then our research work. It's like 40K lines of code, of C code. It's available as LGPL. And we have people starting to contribute a bit from projects which we work with. It's quite actually well known as a state of the art. We have a few hundred citation of the ground articles, so it's quite well known nowadays. So just to give a concrete idea of how it works, so we have here data A and B, which is known to StarPU. A is still in the main memory, while B has been pushed to the GPU already for some reason. And then when the application submits a task, the scheduling engine decides where to schedule it. So here it will decide to push it on the GPU. It will take some time to bring the data A to the GPU, but probably the computation will take less time, so we do this. And it tells the memory management that we will need A and B on the GPU, so it will push the data from the main memory to the GPU and invalidate the copy which is in main memory since we modify A. So the copy in main memory will not be valid anymore. And then it computes and it terminates. So the interesting part for you mostly is the kind of optimization that we do automatically, and thus the requirements we have on the graphical stack. So we do task pipelining. That is, we push several tasks in advance to the GPU so that it's always kept busy with computing things. We do the task execution and data transfer overlapping. So we prefetch actually the data into the GPU while some tasks are already running. And we also support direct GPU copies, well, at least when it's supported by the drivers behind. And so, and who knows what we would like. At least since we have this task graph, there are a lot of things that we can do. And so the graphical stack can provide us as a support, the most we can exploit it. So the main thing we really need is asynchronous API. For instance, we have had a lot of issues with the Intel implementation of OpenCL. Maybe it's an old version, but it was really not working with asynchronous versions of the API. We really need this just because we want to pipeline tasks, we want to overlap things and everything. And with fine-grained synchronization, when there were early versions of the Xeon Phi, we discussed about data transfer termination. They were providing us a barrier over all transfers that have been scheduled yet. We told them, no, we don't want this. We want to be able to wait for this transfer and not another. And they would tell us, but it's expensive. Fine, our data are like a megabyte or 8 megabytes long. We don't care about a microsecond overhead. So just give us the possibility to have the fine grain if we want, and maybe sometimes we don't want, and that's fine. But provide both approaches. And when I say asynchronous, I really say asynchronous, that is non-blocking. In CUDA, we have seen that sometimes when we try to push too many prefetches, asynchronous prefetches, at some point it will not tell us that it's busy and cannot take in more of them. It will just block. And that's a problem because then we don't know how many we can push in advance. That depends on the card maybe. I don't even know, and I don't want to know. Just provide me an error core or whatever so that I can say, okay, I will hold back, wait for some transfers to finish, and then I will push some others. And that will work fine. For now, we don't have this in CUDA, so we say, okay, let's push 20 transfers in advance, and hopefully that will be fine. That's not a good thing. Just don't lie and provide the information. For matrix, multiplications, etc., we need the pitched 2D copy and 3D, etc. That's really nice for us. Maybe 3D is not so useful because we can just submit several 2Ds and that's fine enough. But really 2D is important because we quite often take just a part of a matrix. And we need thread safety. Mostly none of the implementations of the library that we have is really completely thread safe. We have always had to put some mutex or only call the functions from that thread because we know that we have problems with concurrent accesses on CUDA streams, for instance, or some other kinds of things. And that's really a pain because you have a task which has finished on the CPU, and you know that you have to push the data from there to a GPU. And nowadays we have to tell this thread which is handling the CPU, the GPU, when you have time, please push the data. Well, we could issue the transfer from that CPU and avoid that cross-CPU synchronization. So ideally, it would be just thread safe. Just on the side, the host memory mapped on the GPU and vice versa, so you map some host memory into the GPU or vice versa. It's expensive, yes, but it's extremely useful because quite often, for instance, you in a kernel want to contribute a result into a big data, and you don't want to manage the transfers just because it's complex. And actually, you just write one float and, okay, it takes a microsecond, 10 microseconds, that's fine. We don't have so many of them to transfer. And doing it another way would be really complex. So it's fine to provide this. It's really helpful. So the programming interface, we have actually several of them. And so it's interesting to discuss a bit. So the C interface, basic C interface, you have an array in the main memory. which is initialized. And so what we do is we register this array and we get a handle. And from now on, when it is registered, you're not supposed to access the data through the array because maybe StarPU has already pushed it on the GPU. You never know. So you just use the handle, and when you're finished, you would unregister it. And then you have the notion of task, but one thing that we have introduced before that is the notion of codelet. A codelet is just a super function. That is, it knows how many data there are, how they are accessed, and the various implementations. So basically, it's just like a function prototype, except that it has several implementations. And then issuing a task is simply taking some data and taking the codelet and then submitting the task. You may have some parameters on the side, but basically it's like this. And you can submit a lot of them, wait for some of them, submit others, etc. It's completely dynamic, actually. So that's one way of doing it. Another way is an insert task helper, which is basically the same, except that it's just in one function call, so it's nicer. It's mostly some sugar. So the codelet and then the data. And then we have also tried to tinker with GCC to have some more language-like task submission. So here the idea is that we have a prototype which describes a task. So it has the attributes task to express that this is not a function, this is a kind of super function. And then you tell that this function scale vector CPU is an implementation for the scale vector task. And then you provide the function which actually does the work. The nice thing is that this will check all the parameters in a nice C way. And then in the application you have the usual data. You have to register for some technical reasons. But then you just call the function. It's not actually a function, it's a task with just the data as a parameter. And then you can wait for it. So it becomes really natural, and you have the same idea of I have these two other functions which take input as an input, and this one was writing to it, and then we have a dependency between the scale vector and the prop vector and the shred vector, and these two can happen in parallel. So in the end, you really end up with the nice source code I've shown at the beginning. For OpenCL, it's not so simple because you have to decide the group size and things like this, and push the parameters to the kernel, etc. It's complex. So we have thought about just using a pragma which would generate all of this, and just giving it the name of the function to generate the file in which the implementation resides, and the name of the function to call. And then, of course, the group size, etc. So just to give a couple of numbers before concluding, this is a kind of results that we get. So we have bigger and bigger matrices, so it gets more and more efficient. And we have results with 1 GPU, 2, 3, and 4 GPUs. So you see that it scales quite linearly with the number of GPU. For big sizes, of course, with just small matrices, you don't really benefit from from a lot of GPUs. And the interesting thing is when you not only use GPUs but also CPUs, you get an increase which is like worth a GPU power. And the interesting thing is that the additional performance we get, 200 gigaflops, is actually more than what you would get with CPUs only. That is, it brings more than its own computation power. How is that possible? It's simply thanks to heterogeneity. What actually happens is that we offload some computations from the GPU to the CPU. That is, we have some performance depending on the kind of task that we have in our application. And some of the kernels are really faster on the GPU and some others are not. And StarPU, its scheduling engines, actually notices that and will tend to push these on the CPU rather on the GPU. So we actually get the GPU free of all these tasks, it's not so good for. It's faster than the CPU, but not so good. And so the CPU handles them, and then the GPU can spend most of its time on the really efficient, the task for which it's really efficient. And so in the end, we have a super linear effect, thanks to heterogeneity. So to conclude, tasks are really a nice programming model, which serves as a playground for a lot of things that we do, also runtime, scheduling, algorithmic, etc. And we have been able to implement a lot of applications on this. Sometimes we lose a bit of performance, parallelism, etc. But in the end, we gain so much from automatic execution on the architecture, automatic pipeline, and overlapping, etc. that in the end, we actually get more performance than the previous implementations. So that's what we do then. We can experiment with various scheduling heuristics to optimize completion time, memory consumption, energy consumption, etc. Thanks. So are there any questions about this?
Question? Okay, thank you.
Okay, thanks.